let's talk about some stuff. I wrote a library. Let's talk about it. Good? Okay. I wrote a library. It's called Vivid. It does sound synthesis, and it's in Haskell. If you'd like to follow along at home, you can go to Hackage. It's called Vivid. And you can just also Cabal unpack and look at it directly. Yeah, right. You shouldn't be following along by actually making music right now, but you will need supercollider to use this also. But supercollider, Vivid, and GHC is all you should need. So let's see. This is an unfamiliar machine to me, so it might take a second. So supercollider and sound synthesis. Supercollider is an application which looks like this. One second. It does music processing and other audio things. Oh no, it doesn't look like this. We're just running it. There we go. Right now, it just looks like this. But it's a great application. It's got its own built-in programming language called supercollider, and it's a great way to make music and sound. But so is Haskell now. The first thing I want to just start for anybody using this is, when you're learning Vim, the first thing you learn is the escape key just to get you out of any problems. With Emacs, it's Control-G. Here it's Command period, and this is kind of a pun. So usually you run stuff in the REPL with Vivid. In supercollider, the application, you literally hit Command period, and it will just stop everything. So if you've created some sound that you can't stop, Command period becomes pretty second nature. And now we've got the version of that too. So the primary feature of supercollider, arguably, and the primary feature that makes it interesting to us, is that there's a server-client split. There are two completely separate applications. One is a server, which runs very heavily optimized sound synthesis code, and a client which runs all the coordination and music creation. These communicate over UDP or TCP, which means we can just completely rip out the client in supercollider and connect with Haskell and send messages to the server. So this is a lot of what we'll be talking about today. This is synth definition. Synths are musical code which runs on the supercollider server, and they have sort of like classes in object-oriented programming. You have the general class, you have the synth definition, and then you have instances which you run, which actually generate sound. So this here is a synth definition. I'll walk through a few interesting features here. So we've given it a name called full synth def, which is optional. We've also got, obviously, a Haskell reference to it. We have some arguments, frequency right there, with a initial value, not to be confused with default. It can, yeah. Okay. So this is a name that the supercollider server will use to identify the synth definition. We refer to it with full synth def, the Haskell identifier, and the string name is optional. We've got frequency as an argument to our synth definition, and you can see we refer to it here. So it's got an initial value of 100, and so that gets plugged in much like a lambda that's got a variable reference. And we'll go into the rest of what this means later. but this is really what we'll be getting into. So UGens, unit generators, are this here and this here. These are the small optimized pieces of code which run on the server and actually either generate or process sound. Cool. So sound, let's make some sound. So that was... So this should be the same as what we were just looking at. Oh, okay, fine. This is a step that you don't usually need to do. This is some weirdness about this computer. So we'll load full synth up. And now you'll be able to see we've got a synth def here. And we can initialize it with. So this is how we turn a synth def into a synth. And then we will want to keep a reference to it. Okay. Well, wasn't expecting that one. That's weird. You'll just have to take my word for it, I guess. No, the server is still running. All right. Well, I suppose I can walk through this all without. And you'll just have to believe me. Just give this another shot. Well, I don't know. So this makes a cool sound. You'll just have to imagine it. So it won't sound as cool. Oh, I had just done that, but I'll do it again. I'll kill the server too. Sorry? All right, so load the examples. Oh, need to explicit. Okay, that'll be more interesting for you all. Okay, so we've got a synth. It's making sounds. And we've got a reference to it now. Node ID. So this is a reference to the executing code on the server. So we can free it when we're bored, and it's gone. All right. So an implicit thing which happened here, which you may want to do for efficiency, is you may want to actually define the synth def before you use it, and that's done. But to us in GHCI, it looks the same. Sure. Also, is the font size large enough for everybody? Okay. Bigger? All right. You asked for it. Cool. Okay. So define SD synth and then set. So then let's set a value. So we've got the frequency argument here. That's the initial value. If we want to set it to be something else, it changes instantaneously. And then the identifier stays the same. Okay. So another thing that this library has is named parameters. Some people don't love it. A lot of people do. So here we're explicitly naming our frequency argument is called freq, width is called width, etc. A nice feature of this is that the type of, for example, varsaw is frequency to width. So if we're typing things up quickly, it's very easy to see what we need. Some people might be disturbed by the strings everywhere. And so this is pretty much everywhere where you could end up with a string. I understand it's a little concerning that there's sort of some stringly typedness going on here. I've chosen to do this because I'm really optimizing for speed of a person typing. Like a person's playing music on stage, they want the fastest way to get an identifier. And also, this allows us to get the variable names without using any template Haskell, which is nice. And if you really hate it, you can do this, and look, there's no more strings anymore. So if you just define strings to a variable, it's all type safe, right? So we can all have what we want. So another thing that might look strange to the average Haskeller is how we're passing all different types of things into these arguments, or to these functions, right? So we're passing a float as a frequency, we're passing a string as a frequency, and then as another argument, we're passing the result of a computation here. There's a type class, toSig, to signal, and then toSig m. And so this do block here is just a state monad, nothing else, nothing fancy. I resisted the urge to have my own, synth-def monad. It just constructs a graph. So it's pretty easy to have things which append, and if we have something like a string, we basically just return to get it in the monad. So you're likely to see all of these different forms in some code, and they're all valid. So you can have arbitrarily large synth components inside an argument. Okay. We have some math operators. The tilde is the mnemonic for that. Is it looks like a sound wave. They all work how you would expect them to work. So there's a couple reasons. The question was why did I not just make signal an instance of num? A couple reasons. One, stylistic, is that I don't like num instances which aren't complete num instances, and you can't do everything. There are certain things that you wouldn't want to do. There's a historical reason for it. In general, they're not really numbers. There's a lot of things there are a lot of properties which don't hold, and I don't want to lie about it, essentially. But that's valid. Modularity is cool. We're able to, with an SDState, pull it out as we expect we usually can in Haskell, and use it where we like. So, for example, we have a piece here. We can use it in these different examples and use it as we want. So, for example, low takes this sound that we've created and puts it through a low-pass filter and then spits it out. I should explain, this line actually sends it to an output bus on the computer. So the fact that there are two of them makes it be stereo. Oops. And 0 is just the 0th bus, so the left ear. So we've got left and right here. Okay. Oh, it's just a thank you. Okay. That should be, it's the volumes set. Okay, well, we'll command period to be safe. They're pretty quiet, that's the problem. Well, okay. I'll do a little live coding. That always makes talks more exciting, right? So we'll set a volume parameter, and by default it'll be 0.1. And so then now let's create a synth. Can't really hear much. We'll set S volume to be 1. Oh, I see. Thank you. Okay. Thank you. It's an interactive talk. Okay. All right, it's pretty quiet. I didn't have time to sound check any of this stuff before the talk. Sorry, you'll just have to believe me. But hi, you heard that there was something. Okay, fine. Okay. Anyway, there's plenty more examples. Oh, we already have buffers? Okay. If anyone has any questions, now would be a good time, because it looks like I'm further ahead of schedule than I thought. This one should... Yeah, go ahead. That's a good question. Right, that's why that didn't work. So what you'd want to do is like that. Okay. Make a synth. There were a lot of tech issues. Okay, so this now we've got high. S synth. Create the connection, and now we'll set. Okay, it's still a little faint, but there we go. Yay! By the way, I have to promise you all, I've used this a lot on multiple machines of my own, and it works beautifully. This is all presentation, issues.
Yeah, you gotta give Tom credit. He's using my messed up machine for this due to a technical issue. So.
Yeah, give me credit, guys. No, that's fine. So then this should work now. So here's another one. Here's something slightly musical. We, instead of setting a frequency, we're using MIDI CPS, which goes from a MIDI note number. Everybody knows, like a MIDI keyboard. It sends signals. It sends numbers 0 to 127. Each represents a half step, so like a piano key. And so we can use the function MIDI CPS to convert from a MIDI number, which is much nicer to work with because you can add and subtract integers, and it converts it to a frequency that we would actually want the server to be using. So here we just give it a note number. We create a sine wave, just a basic fundamental sine wave, and we make it quieter, and we send it out. So as simple as it can get, pretty much. But then we've got, we start using 4M and more interesting things. So we've got these 4 notes here. As you can see, like anyone familiar with music can see the relationship between the half steps here. And we just define the synth, create it, and then loop, setting it to a different value. So let's see if this works. All right, all right. Sorry, what was the question? Right, so a major feature of this is we're sending all of this over UDP. So the question was, why are we using strings as for argument identifiers? There are a few reasons. I think it's the right trade-off, but but maybe the largest one is that we need to send as a string over UDP the name of the variable. So the easiest way to do that is actually just to use a string to do so. Really, it's the only way without getting into template Haskell. And template Haskell, from experience, template Haskell and performing music live really don't go hand in hand. So this is really, I find, the right trade-off. So okay, let's see if this works. Okay, music, right? This sounds more musical. And then we just command period. Okay, so let's see, are there any others that I skipped here? Unfortunately, there's a couple that I won't be able to play involving buffers. Buffers are great. They're just basically an array of floats in the supercollider server. So they're really nice for example, storing and recording sound, like natural sound. So if you want to make beats or do effects on vocals or things like that, buffers are a good place to start. These are some functions for those of you following along that you may want to use. Make buffer from file, which just reads an audio file, and then you can start sampling with it. Play buff 1 and record buff 1. Record buff takes an arbitrary signal, so maybe a microphone, maybe a synth that you created, and records it into a buffer. Play buff plays it out. Unfortunately, I don't have any example files on this computer, and I really don't want to play with live mic input into this at the moment. I can at least show you what it looks like. So here's a little polyrhythm thing. These are the files which make it difficult to use at the moment. But so we load a couple of files, a snare drum and a hi-hat. We define a synth def, play sample, which as you can see is pretty simple. We take a buffer ID. Buffers are referred to IDs just like nodes are referred to node IDs. And we call play buff on it, and then we multiply it by a volume. It's pretty much as simple as you can get. Does anybody have any questions about sort of the structure of this, or like does anything not make sense about it? Yeah, sure.
Sorry, like this is for beginner.
Sure.
So, in the do notation, like discarding environment,
What? So why am I discarding this here? Okay, so synth returns a value, which is the node ID, and GHC will complain with a little warning if I if I have a function which returns a value that I discard, unless I explicitly discard the value. So this is just a way to do that. Any other questions? Okay. So all right. So we play. You'll have to believe me that I can play a sample, and then we have a little polyrhythm here where we play a snare. We wait. Our tempo is set to be 60 BPM, so we wait half a second in this case, but we wait half a beat basically. Then we play another snare and we wait half a beat, and so we do that, and at the same time we wait a third of a beat and play 3 hats. So it's have a polyrhythm going. And if I had these files here, you could hear it. But I just want to show you it's not difficult to make actual music here. There's an interesting rhythm going on here. We get to use everything that Haskell gives us. Fork.io is free. STM is free, which is really nice. I use it a lot for musical things. And so there's not a lot of overhead here just because we're making music instead of generating JavaScript or something. Musical timing. Turns out thread delay is pretty awesome. Just control.concurrent.thread delay is fine for actually playing music, which I was surprised about. There are more sophisticated solutions. Supercollider lets you explicitly define timing at which messages sent to it should execute. That's better, but it requires a lot more bookkeeping. And thread delay is great, so I can literally so sleep here, which I've defined in the top level module, it just literally multiplies by 1,000,000 because it's microseconds and from enums. So you just give a number of seconds and it calls thread delay, and it works great. So the other thing regarding musical timing is some operations are not free time-wise. So for example, defining synth definitions for a large graph of unit generators, it can actually take a noticeable amount of time to define. So you're going to want to either front-load your definition of synths with an explicit define SD, or you're going to want to fork a thread to be doing them. But it's possible, if you're not careful, to get yourself in a scenario where if you're playing a song and then halfway through a new synth is about to be played, that synth may miss its mark timing-wise if you haven't preloaded that synth. Don't lose your node IDs. This is, so our node ID is a reference to something happening on the server. If you lose it, command period is really your only recourse. So it's, it's something to look out for. I do it pretty often, and I use command period a lot. Free is, I have been using, I think. Well, anyway. Free will kill a running synth, and it will kill it instantaneously. So, for example, if you have a wave, right, a nice sine wave, very simple, and you decide if you call free right here, instantly the speaker cone, like we're pushing actual air here, the speaker cone is going to go from the top to 0. And that can make an audible artifact. So there are a few things that we use in supercollider to do this. The simplest of which is lag. Lag takes a value and creates a continuous line from its current value to its new value. So I've got two examples here. The first is lag volume. So let's look at that one. And then there's lag pitch, which will do the same thing, but for pitch. So lag volume here, we've got a synth depth. Oh, this is old. 1 second. These are not needed anymore. Make sure it still compiles. Live coding is more exciting, right? Okay, cool. So we've got a sine osc. We start with a simple sine wave. There are more exciting ones, but it's fast. We make it quieter, multiplying by 0.01. We then well, that's wrong. Oh, no, that's fine. So signal, we bind signal to this sine wave, and then we multiply it by a lag, which takes the volume argument as its input, and sex is the amount of time that it creates the continuous function over. So we lag our value. If we make a change in volume, it will take 1 second to go from the old value to the new value. And you can ignore the KR for now. I'll explain it in a minute. So we multiply the lag in the volume by the signal, and then we spit it out to the speakers. And so you can imagine if we didn't have the lag here, it would just simply, you'd be multiplying signal times and then the string volume. So all right, so S is a synth of lag vol. And we're passing it no arguments at the moment because so its default argument will be 1. So if we don't give it an explicit value, it's its default 1. All right. This computer is a special snowflake. You don't usually have to do that. So we'll explicitly connect, which you don't usually need to do. Okay, there. It's just a sine wave with a volume. And now if we set volume of, we'll double it. It's going to get louder. You can hear it grow over time. Takes a minute, takes a second to get there, right? So then the obvious thing to do is you kill it, and then you free the synth, and you don't get the clipping sound. You can also use lag for pitch. It's a nice thing. A lot of synths sound better if you don't immediately jump. So very similar, except well, not that similar. I'll walk through it. Or unless, is this obvious to people, or should I walk through it? Walk through it. Great. Okay, cool. So we're making a synth. It has one argument, which is the note number. This is the MIDI numbers again. It defaults to 0, which is pretty much inaudible. And so then the first thing that we do is we create the lag value, the note number. So we get a frequency with MIDI CPS. And then we lag the note number over 1 second. So if there's a change in the note number, it will be delayed over a 1 second period. And then, so we use that L, which is the frequency at any given time, and we pass it into the frequency argument of a sine wave, and then we multiply it to make it quieter. And then the last line is usually always the same, just putting it out to the speakers. Does that make sense to people? Yeah, the question mark KR is to change the rate at which it computes. We'll talk about it in a minute, but that's the short answer. Other questions? Okay, so let's make one. So we'll do S is synth lag pitch, and we'll make it be 60. Oops, no, that's totally wrong. Note num is 60. Okay. And it's just a simple sine wave. And then now let's change it. Okay, doesn't sound awesome on these speakers, but works well, right? And then, okay, so then we free this, and if we're lucky, we can hear the clipping that I was talking about before. Yes, there's a little clip going on. Okay. Cool. Any questions so far? Okay. Calculation rates. This is what we were talking about a second ago. Supercollider is really tuned for efficiency. The server is really tuned for efficiency. There's basically two ways which sound generators can be run. There's one, a rate at which you can actually hear audible sound. So like a CD is sampled at 44,000 roughly samples per second. Supercollider is a little bit higher than that. And so anytime you have, for example, a sine wave, it's got to be emitting values at 48,000 times a second. A lot of times that's not needed. So for example, here we've got this lag, and we're using the lag as a frequency argument to something else, to a sine wave. We really don't need it to be changing 44,000 times a second. We really only need it to be changing every like half second. But supercollider defines a second rate, control rate, which is very, very fast, but slower than the audio rate. And obviously this saves a lot of CPU cycles, which is nice for real-time music performance. So pretty much everything in my library is AR by default, unless that doesn't make sense for the particular function. If you want to slow something down to KR, put a question mark KR. The mnemonic there is question mark is like thinking, which is like computation. You know, there's not a lot of one-letter identifiers. So occasionally this matters for sound. Sometimes AR actually sounds better. Occasionally, only one makes sense. So for example, you can cause aliasing with AR where a control value has like an aliasing artifact. Are people familiar with aliasing like in imagery? Okay, so aliasing in imagery is you take a photo of a brick wall and the number of pixels allotted for each brick is smaller than the size of the brick or whatever, so you get a weird moire pattern. Happens on TV too, where people are wearing like a striped shirt and it like jitters. You can get the same thing if you're putting too much into something at a higher rate than it's being sampled. So occasionally you actually do care about KR. Typically, if you're using something as an argument, use KR if you care. Otherwise, AR is fine, and that's why I've put it as the default. Okay. Let versus bind. So we've got a state monad, right? And I'm binding here all the time. I'm, A bind this, B bind this. Question might be though, if we can pass in, for example, if I can pass in A here, or if I can pass in A without binding it, why should I ever bind? And the answer is for efficiency, basically. If each time you bind, you actually create a piece of the sound synthesis graph. And so if you don't bind, if you use a let and then you use the same graph multiple times, it'll actually create two instances of it. The other time that you might care is when your unit generator is non-deterministic. Almost all of them are, but for example, we've got a white noise one. So type of white noise is just a signal, right? But we would actually expect two white noise generators to be making different sounds. So for example, here we're using a let. Everyone knows white noise. It's just totally random static. So I create white noise at a control rate, multiply it by 880 so it's audible, and make a sine wave out of it. So we've got a sine wave that's making sounds somewhere between 880 and 0. Sorry, a sine wave whose frequency is at any point somewhere between 880 and 0. Then, on the next line is interesting, we subtract x from itself, and then we just play that, basically. So obviously, depending on whether these two x's are the same, is going to determine whether we hear nothing or whether we hear some jumbled sounds. Let defines an action which has not yet been run. So when we get to the minus here, we actually execute x twice. Once for the left, once for the right. So we would expect to hear something here, and I'll prove it to you. Okay. Okay. You'd think I would learn. Okay. All right. So there, we've obviously created two things. And now, just to prove that I'm not lying to you all, we'll bind instead. And it's inaudible. So I was telling you the truth. Okay. Ooh, this example may not work, but let's go ahead with it anyway. That hasn't stopped me so far. Oh no, this really isn't going to work. So I've written Vivid to be interoperable with supercollider language as much as possible. So people who already use supercollider and have existing code in supercollider should be able to, for example, define synth definitions that they've already written in supercollider and then call them from Haskell, and vice versa. So if you've got some interesting pattern structures in the supercollider language, but you'd rather all your new synth defs are written in Vivid, you can call that, you can totally interoperate. You can call almost as easily buffers between the two. Pretty much each design decision has been made so that you don't step on the toes of another client who's talking to your server. Let's see. So I can't actually show you any examples of this, but I can show you the two main things that allow this to be possible, at least for synths, which is what we're talking about today. One is SD right now. We haven't given it a name, and so we always refer to it just by the Haskell value. When we send it over the wire, we just give it some. The name is actually. So the name is actually Vivid, so it doesn't clash with anything else, concatenated with the hash of the synth definition itself. So it won't collide with anything, but it's not super informative. If you want to do SD named foo, now you can suddenly refer, you can, if I were to pretend that this were a supercollider window, you'd be able to just call like this and execute foo, and then pass arguments as you would in supercollider. The other thing that you can do is, for example, synth, we call synth using Haskell identifiers, but there's something else that we can do, which actually I can demonstrate. We'll call this UL for using let, right? And we'll make it actually emit sound. Undefined, oh. Okay. And so now, instead of calling like this, instead we'll do something like this. Thank you. Well, okay, 1 second. Yeah, I do have to explicitly define it in this case. Thank you. It works. So if I define something from within supercollider, I can just refer to it by the string name. And that's cool. Thank you. And thank you for your patience, and thank you to Doug and Ryan for making this all come together at the last minute. It was a close one. If you have questions, concerns, whatever, I direct you to the mailing list first. Haskell Art is a great mailing list about Haskell and art. There will be a website soon. And Hackage, this is up on Hackage as Vivid. And so if you want to look at the types or look at the code, that's the best place to do it. Thank you.